Today I'm going to talk about my GeoGebra construction, and the topic of the GeoGebra construction is angles subtended at the centre. This angle here stands on this arc and is subtended at the centre, and this angle here stands on the same arc and is subtended at this point C on the circumference. And the mathematical thing that we're going to prove today is that this angle at the circumference is half as big as the angle subtended at the centre. That's always the case. So no matter, as long as you keep A and B in the same spot, you can move point C anywhere you like, and the angle is always the same, and it's always half of this angle. And if you change where A and B are, then you can change the size of this angle, and you change the size of this angle as well. But no matter where you put point C, it's always half, plus or minus surrounding error of course, it's always half of the angle subtended at the centre. Now if you've seen me avoiding putting the angle C down here, if you do that, then you just change the sense of where the arc is. So now the angle is a reflex angle in the middle here, and the angle stands on the arc and is subtended at the centre, and this angle here is now is half still. The angle out here is still half this angle, no matter where you put the angle C, point C. So as you move it around, it just changes the sense of the angles that you're talking about, where the actual angles that you're talking about are. But the maths, this angle is always half of this angle, and over here this angle is always half of this angle. So what we're going to do is go through the proof. So I'll put the applet back the way it was by pressing this button here a couple times. So I press this angle here, this button here, and it puts the applet back the way it was. And we can, well, before we do the proof, we can demonstrate the proof. So you can see that if you take the red angle and you slide one copy of the green angle and another copy of the green angle, and you line them up next to each other, that they add up completely to the big red angle. So no matter whereabouts you put your angle, the big red angle is double the size of the green angle, and that's what we're going to show. So I'll put it back the way it was. I'll put it back the way it was, and we will go through the proof. So the first thing you do is you draw a line from there through there. Well, let's see it. You draw a line from point C through point O, and I've made it stop here, and we're calling this point M. And you see we've made two triangles. We've made this triangle OAB and another triangle OCB. And then you start looking around, and you see that there's this is a radius and this is a radius. And if you go to the other side, that's a radius and that's a radius, and they are all the same length. OC is equal to OB, and that means that you've got an isosceles triangle, because these are the same size. This is longer, and then on the other side, this is the same size as this. And then you say one of the great things about isosceles triangles is that the angles opposite sides that are the same are also the same size. So this angle is the same as this angle, and this angle is the same as this angle. So we're going to use that result a bit later on. Then we are going to say, of course everybody knows the exterior angles of a triangle, that this angle is twice as big, is the same as that angle plus that angle. But what we're going to do is go and have a look at that. And basically we say that on this straight line here, this angle plus this angle add up to 180 degrees, because this is a straight line. And then we'll do some algebra and get this angle by itself. And then we're going to look at this triangle, and we're going to say that this green angle and this green angle plus this red angle are also add up to 180, because that's the properties of a triangle. And then we're going to do some algebra on that. And then we can say that, looking at this equation up here, BOM is equal to that. And we see that written down there, so we can just write, instead of writing that, we can write that, which what we do next. BOM, this angle here, blue angle is the same as that angle plus that angle. And then on the other side, AOM is equal to OCA, that angle, plus OAC, which is that angle, OAC. Now we're going to say that this angle is the same as that angle. So instead of writing that this angle is the same as that angle plus that angle, we can say that this angle is just double that angle. And that works on the other side as well. This angle is double that angle. So now that you understand the exterior angles of an isosceles triangle, you can go back to the original proof and you can just say that that angle is double that angle. And basically the rest of the proof says that that angle is the same as double that angle, and that angle is the same as double that angle, so this angle is going to be the same as double that angle. And that's what the rest of the proof does. So BOM is 2 OCB by substituting that into there and factorising. And then the same on the other side, this angle is the same as 2, this angle is the same as 2 lots of that angle. And then we're going to look at the diagram, we're going to say the big red angle is the same as the blue angle plus the other blue angle. And even if we move it around over here, the big red angle is the same as the 2 blue angles. The tricky part is that if you stick it over here, the big red angle, the red angle is the same as the big blue angle minus the little blue angle. But we'll come to that a little bit later on. The next part of the proof is that instead of writing AOM in here, we can write 2 OCA because we found that earlier. And instead of writing BOM, we can write 2 OCB because we found that out earlier, that that angle and that angle are related. And then we can do some more algebra. And then we can look at the diagram up the top and we can say that OCA and OCB add together and they make the angle ACB. Yep. And back over, if you put it over here, you see that ACB is equal to OCB, the big blue angle, minus the little blue angle. And put it over this side, the names of the angles change, but ACB is, oh no, it wants to be down there. ACB is OCA minus OCB. So the maths works out no matter whereabouts. Oh well, we might as well, for completeness, we might as well do that. The blue angles add up to the green angle. So go back to roughly where we were, and that's the end of the proof. Basically, that AOB, the red angle, is twice as big as ACB, the green angle. And you can demonstrate that, have a play. And you can go back, you can still go back and look at the exterior angles of a triangle. And that's the way that I would use, well, one of the ways that I would use this applet. And you can always click this one to go back to the way it was. So thanks for listening.